Welcome to our video lecture on nuclear chemistry. So we are going to continue our learning about atoms and the structure of atoms, but we're going to focus specifically on the nucleus and some of the changes that can happen within the nucleus of an atom. Our essential understanding big idea for today is that radioactivity is a spontaneous decomposition of atomic nuclei to form more stable nuclei. So sometimes we have atoms and the nuclei will just fall apart, change, and become more stable nuclei that aren't going to decompose. Our objectives for today, we are going to define what is a radioisotope and what is transmutation. We're going to identify different radioisotopes in the periodic table. We're going to state some of the applications of radioactivity, and then we're going to look at different types of radioactive decay. We're going to practice balancing some nuclear reaction equations, and then we're going to end with a big look at Einstein and E equals mc squared. We're going to wrap up the day with a look at half-lives, the rate of decomposition of those atomic nuclei. All right, so to define radioactivity, radioactivity is unstable atomic nuclei spontaneously decomposing to form those more stable nuclei. This is also known as radioactive decay. So radioactive decay, radioactivity, same thing. Atoms are falling apart to be more stable. Transmutation is what happens during most radioactivity. One element will change into a different element, and this breaks everything that Dalton said about atoms of one element cannot change into other elements. The number of protons will literally change in the nuclei because the nuclei break apart. So remember that isotopes are atoms of the same element with different numbers of neutrons. Radioisotopes are those isotopes that are radioactive. So lots of elements will have some isotopes that are radioactive. We have about 1,500 different isotopes that we know. Only 264 are stable. The rest are all radioactive. So how do we know if an isotope is going to be radioactive or not? If we're looking at small atoms, atoms that are less than 20 protons big, so calcium and down, then if we have equal numbers of protons and neutrons, we're stable. So proton equals neutron means stable when you're small. So carbon has 6 protons, always will have 6 protons. Carbon 11 has a mass of 11, which means 11 minus 6 is 5 neutrons. 6 and 5 are not equal. This guy right here is radioactive. How about carbon 12? Carbon 12, again, 6 protons. 12 minus 6 means that we've got 6 neutrons. 6 and 6 is a match. This guy is stable. What about carbon 14? Again, we have 6 protons, which means 14 minus 6 is 8 neutrons. 8 and 6 are not a match. This guy is also radioactive. What about the really big elements? Elements with atomic numbers that are greater than 83, 83 protons and bigger, are simply too big to be stable. So everything polonium on up, these guys are all radioactive. They're simply too large to be stable. Well, what about the guys in the middle? So now, if we have more neutrons than protons, we are more stable. So the small guys, we want it to be equal. Big guys, doesn't matter. Guys in the middle, more neutrons means more stable. So zinc, zinc's atomic number is 30 protons in all of these particles of zinc. So 55 minus 30 means we have 25 neutrons. There are fewer neutrons than protons in this one. This guy, radioactive. How about zinc 60? Again, we have 30 protons. 60 minus 30 is 30 neutrons, equal. If zinc were small, this would be stable, but because zinc is a middle-sized element, this is also radioactive. How about zinc 64? 64 minus 30 means we have those 34 neutrons. 34 is greater than 30. We have more neutrons than protons. This guy, stable. So what can we use radioactivity for? What are some of the applications of radioactivity? Well, we, of course, can make some power. So here are some nuclear power plants. We also can use radioactivity in medical diagnostics. These X-rays were made using radioactivity. Geiger counters, of course, use radioactivity. What we can do, what's happening in this picture, is we can actually add a radioactive isotope to oil in a pipe. And then we can use the Geiger counter here to detect where the leak is by finding that radioactivity. What in the world is this? So we have a source of radioactivity that sends out some beams, and as long as the beams hit the other side, we're golden. But if the beams are deflected around, we have a big alarm go off. This, my friends, is a fire detector, smoke detector. Smoke detectors let us know, because of radioactivity, if there's smoke in the air or not. And then, of course, we have weapons. We have atomic weapons that are hugely destructive. Now we're going to look at different kinds of radioactive decay. The first one we're going to look at is alpha decay. Alpha decay is a kind of radiation in which a helium nucleus is emitted from some radioactive source. This nucleus, this helium nucleus, is called an alpha particle. It has 2 protons and 2 neutrons. So it's a helium nucleus. It's going to have 2 protons, and if it has also 2 neutrons, it's going to have a mass of 4, because 2 plus 2 makes 4. It has a charge of +2, but since we're focusing here on nuclear chemistry, we don't really care about the charge. We don't care about those electrons at all. So this written all by itself is an alpha particle. Sometimes we write it this way, and I don't know how that got lost from the slide, but it could be that 42He, or we can use the Greek letter alpha. So He or alpha, this is our alpha particle. Sometimes we can have something like this piece of polonium, and this alpha particle just flies out of the nucleus because this guy is not stable because it's really big. To balance this equation, to figure out what else we form, I like to draw a line down the arrow. This arrow is showing us reactants and products of this nuclear reaction. We need to balance the bottom numbers and the top numbers. So I like to start with the bottom. Here I have 84 on this side. Over here I have 2. 84 and 2 are not a match. So I need to add something here to balance out 84 and 2. So I'm going to add an 82. So 82 plus 2 is going to give us that 84. So the bottom of the reaction is balanced. We have to do the same thing for the top. So here I have 212. Here I have 4. Definitely not a match. So I'm going to take that 4 away from 212 and we get 208. 208 plus that 4, 208 and 4 makes that 212. We have a match for the top. But now, of course, I'm missing what even is the symbol of this particle. So I'm going to look at my periodic table. What is element number 82? 82 is lead. So this is how we're going to finish balancing this nuclear reaction. I have 82, 208. Lead is going to be the other particle formed when this alpha particle flies out of this atom of polonium. Polonium is going to turn into lead, which is kind of crazy sauce. And this right there is our alpha particle. A second kind of radioactivity is beta decay, and we can show that with this Greek letter beta. Beta decay is going to blow your minds, my friends. It's a kind of radiation that consists of fast-moving electrons that are formed from the decomposition of a neutron in the nucleus. The neutron decomposes into a proton, which stays in the nucleus, and an electron, which is released. What happens is this. We've got this nice neutral neutron. And it's neutral because it has a balance of negative parts and positive parts. Those balance out to neutral. In beta decay, this negative part of the neutron flies out of the neutron. And when it flies out of the neutron, it's now an electron. What's left in the neutron is only the positive part. And that positive part, my friends, is a proton. So our neutron turns into a proton and an electron. The electron flies out of the nucleus, the proton stays there. So here is a little picture of beta decay. So we've got this atom of carbon 15, so 6 protons, 15 minus 6, we had 9 neutrons. And what happens is that one of those neutrons is going to turn into a proton. One of these neutrons turns into a proton and an electron. The electron flies out. We now have an extra proton the neutron that turned into a proton, which is why our atomic number goes up 1. So we went from 6 protons to 7 protons because one of those neutrons turned into a proton. So we went from 6 to 7. But our mass stays the same because the total number of protons and neutrons stayed the same. We just turned one of those neutrons into a proton. And we've got that electron flying out. These fast-moving electrons are called beta particles. We can use that Greek letter beta to show that. Carbon-14 is probably our best example of beta decay. It's going to emit one of those electrons when it undergoes radioactive decay. And this is the unbalanced equation showing that. So let's see what happens here. I have, again, my line through the arrows. I can balance out left and right. 6 on the bottom, -1 on the bottom. How do I balance out 6 and -1? Well, I need a 7. 7 minus 1 equals 6. So I need a 7 on the bottom. On the top, I have 14 and 0. That's just going to be a 14. 14 equals 14 plus 0. What's element number 7? That's nitrogen. So we're going to make nitrogen 14 from carbon 14 when it goes through beta decay. And then this is what we use to show our beta particle. E for electron, -1 because the charge is -1. It's like we have -1 proton because it's negatively charged. Weird mass number of 0 because remember that we kind of round our masses of electrons down to 0 because they're so tiny we consider them to be negligible in mass. And if that wasn't enough, now we're going to talk about positron decay. Positron is sometimes also called beta positive because positrons are basically electrons with a positive charge. Oh my goodness, electrons that have a positive charge. So positron decay occurs when a proton spits out a positron, which means that it loses its positive charge and it's left to be a neutron. What? I know, right? So we're going to have a proton in the nucleus. That proton is going to spit out the positive part. This is now what we call a positron, basically a mass of 0, charge of +1. There's our positron. But because the proton lost its positive charge, all that's left is neutral. It's now a neutron. The proton turns into a neutron when it spits out a positron. What's crazier, even yet, this is going to sound like science fiction, but it's fact, positrons are antimatter. And when these positrons run into electrons in the environment, they make that gamma energy that we're going to talk about a little bit more in a couple slides. So here's an example. We have this nucleus with 1, 2, 3, 4 protons, but this proton is going to spit out that positron and turn into a neutron. Crazy sauce. We can balance equations the same way that we always do. I've got 6 on the bottom here. I have a +1 over here. I need a 5. 6 equals 5 plus 1. So now I have 6 on both sides. 11 on the top. I'm going to need 11 on the top of this guy because this 0 doesn't change anything. Element number 5 is boron. So we can turn carbon 11 into boron 11 when it emits a positron particle. All right, so in beta decay, we spit out that electron. In electron capture, we're going to suck an electron into the nucleus. An atom's own electrons are going to get pulled into the nucleus. And then, kind of opposite that beta decay, that electron is going to fuse with the proton and negative plus positive turns into a neutral neutron. Electron plus proton makes neutron. So here's an example of electron capture. I've got this particle of potassium. Notice that we have the electron, that beta particle, on the left side. Those couple slides ago, it was on the right. Now it's on the left. We're going to add an electron to this potassium atom. 19 plus -1 is 18. We've turned potassium into argon. Let's balance this one. Again, here's my beta particle, my electron, that I'm adding into the nucleus. 13 plus -1 is 12. 26 plus 0 is still 26. Element number 12 is magnesium. We just turned aluminum into magnesium. And then here's another example in picture form. Here's this electron getting smushed in. This proton is now a neutron, and instead of having 1, 2, 3, 4 electrons, we only have 1, 2, 3. Beryllium becomes lithium. All right, so gamma radiation, I mentioned this a couple slides ago. Gamma rays, there's no particle here. This is just big energy. So radiation energy, this big energy is released during alpha decay, beta decay, also during fission and fusion that we're going to talk about on the next slide. So this is how we show gamma. It's a Greek Y-ish shaped letter, and this just says lots of energy. So here, 42He, remember that this was my alpha particle. So this is an example of alpha decay. Thorium turns into radium, and this alpha particle is alpha decay. And also lots of energy. So gamma just says oodles and oodles of energy released. I just mentioned fission and fusion. We're going to look at those two guys. How I remember the difference. Fission sounds a little bit like split. They have that same I sound, fission and split. So in fission, we're going to take something really big like uranium-235, and we're going to smash it with this neutron. This is a neutron. We're going to smash that uranium with a neutron, and we're going to turn that giant atom into a couple smaller atoms, strontium and xenon. What's kind of cool is that we also have some extra neutrons, and those neutrons are going to go smash into more uranium atoms, which is going to turn into more strontium and more xenon, which will make more neutrons, which will smash into more uranium. And we call this a chain reaction. So when you have maybe in movies with nuclear meltdowns, maybe you've heard of chain reaction. This is a chain reaction. These neutrons can become these neutrons that smash into the uranium to make the reaction happen, but then the product of the reaction can make the reaction happen again and again and again. Fission is splitting big things into smaller things. Fission is splitting. Opposite that is fusion. And so fusion, I remember that U in fusion kind of sounds like the U in glue. Fusion and glue. So in fusion, we're gluing things together. We're taking littler things and we're making something bigger. This happens in the sun. This is how we get energy from the sun. We have two smaller hydrogen atoms that are glued or fused together to make this bigger helium guy. Let's look at an example of an equation. We're going to balance it, and then you're going to tell me if it's fission or fusion. So I'm looking on the right side first. I have 56 and 36 and 3 neutrons that each have a charge of 0. So 56 plus 36 is going to give us 92. 92 on the bottom. On the top, I have 142 and 91. I have 3 neutrons that each have a mass of 1. So I actually have a total of 3 here. 142 and 91 and 3 add up to 236. That's a big mass. I'm going to look at my periodic table. I'm going to find element number 92, and that is uranium. So uranium-236 can get smashed by a neutron and split into barium and krypton. This guy up here was uranium-235, and it's smashed into strontium and xenon. So we can have different products from different isotopes of uranium's fission. This one, hopefully you noticed, was another fission reaction. All right, so we're going to practice a little bit. So we're going to balance the bottom. I have 7 and -1 here. 7 minus 1 is a 6. On the top, I have 14 plus 0. That's a 14. Element number 6 is carbon. So we have a balanced equation now. I want you to figure out what type of radioactive decay is this. Hopefully you're looking at this guy and you're like, that's totally a beta particle. So I smashed that electron out of a neutron, and the neutron turned into a proton, which is why I have more protons now. That's beta decay. Let's look at this next guy. We have uranium-92, we have thorium-90. To balance out left and right, I have 92, I have 90, I need 2 on the bottom. 238 on the top, 234 on the top. I need a 4 to balance out both sides. Element number 2 is helium. This is alpha decay. That's an alpha particle right there. But what about this crazy guy? What is this? That's gamma radiation. We also have a bunch of energy being released during this alpha decay of uranium-238. Let's look at another one. I have 8 on the bottom, 7 on the bottom. To get 7 to balance out to that 8, I need a plus 1 here. On the top, I have 15 and 15. I need a 0. This is kind of weird. What has a charge of plus 1 but a mass of 0? Hopefully you remember this a couple slides ago. This is a positron. This is positron decay. Good? All right. We're going to do some more practice. Feel free to pause the video, do these on your own, and then come back and check your work. Get ready, get set. Here we go. 15 on the left, -1 on the right. I need to balance those out. I need a 16. 16 minus 1 is 15. On the top, I have 32 and 0. 32 is going to balance that out. What's element number 16? That's sulfur. So we turn some phosphorus into sulfur. In this guy is a beta particle. This is beta decay. Let's do the next one. I have 47 on the bottom and 46 on the right. I need a -1. 47 minus 1 is 46. On the top, 105 and 105. That's easy. That's a 0. What's -1 charge and a mass of 0? That's an electron. Another beta particle. Does that mean that this is also beta decay? Be careful. The answer is no. In this first example, the beta particle was on the right side. The electron was produced. That's beta decay. On this second example, the electron is on the left side of the arrow. We're adding that beta particle to this silver to turn it into palladium. This is electron capture because we're adding the electron, we're not producing it. We're adding the electron on the left, not producing it on the right. Beta decay, electron capture. Be careful, they look a lot alike. All right, let's do this next one. I already know that this guy is positron. So there's our positron decay. Let's go ahead and balance it. +1 and 20 makes a 21. I have 40 and 0, 40 on the top. Element number 21 is scandium. Capital S, lowercase c. One more. Again, left and right, I have 92 and 2. Oh gosh, sorry, 94. 94 and 2. That needs to be a 92 to balance it out. On the top, I have 244 and 4. I need 240 to balance that one out. Element number 92 is uranium. This guy tells me I've got some gamma radiation. This guy right here tells me that this is alpha decay. Good. So things are about to get super exciting. We are going to talk about Einstein, and this quote is a magical Einstein quote. And we're going to talk about mass defect and binding energy and the quintessential equation here, E equals mc squared. So we're going to talk about what this even means, E equals mc squared. So what's kind of crazy about this idea of a nucleus? The nucleus is composed of neutrons and protons. Protons are positively charged. Positively charged things do not want to be stuck to each other. Positively charged protons are going to repel each other. And so what happens is we have a little bit of, are you ready for this? Mass that turns into energy that holds the nucleus together. And we know this because when we measure the mass of a nucleus, the total mass of a nucleus is going to always be less than the sum of all the protons and the neutrons in the nucleus. So I put all these protons and neutrons together and I add up the mass, but the mass is less than it's supposed to be because some of the mass turns into energy that holds that nucleus together. What's interesting is during radioactive decay, because we're taking pieces apart, that energy that used to hold the nucleus together gets turned back into mass in those protons and neutrons. Crazy sauce. So the E in energy is what that guy is right there. And the M in mass is what that guy is right there. The mass that we lose when we build nuclei is converted into the energy that binds together the nucleus. That amount of mass that's lost is what we call the mass defect. It's the difference between what the nucleus ought to weigh and what it really does weigh, mass defect. And this is the amount of mass right there that we turn into energy that holds the nucleus together. So now let's go ahead and use E equals mc squared to solve a problem. So we're going to find the mass defect, that is the difference between what the nucleus ought to weigh and what it really does. We're going to find the mass defect of copper 63. The actual mass of the nucleus is this. So this is what it really weighs. We're going to find what it ought to weigh, that composition, when we're looking at the combined mass of its protons and neutrons. So copper is element number 29. I'm going to take those 29 protons in an atom of copper. I'm going to multiply by the mass of a proton, 1.00728. That adds up to 29.2112 AMUs. Now I'm going to find the mass of our neutrons. It's copper 63 minus those 29 protons. Sorry, 63 minus 29 protons leaves us with 34 neutrons. 34 neutrons in this particle of copper. So 34 neutrons times 1.00867 AMUs per neutron gives us a total mass of 34.29478 AMUs. So if I add all the protons and all the neutrons, we get the mass of what the nucleus ought to be, all the protons and all the neutrons. So when we add these up, we get a total mass of 63.50590 AMUs. This is what it ought to weigh. But in reality, it has this mass. So the actual mass is 62.91367 AMUs. This is the actual mass. So the difference between what it ought to weigh and what it really does weigh turns into 0.59223 AMUs. This is the mass that was lost when it went from being a mass to energy, holding the nucleus together. This is our mass defect. This is our mass defect. It's the M in E equals mc squared. So now we're going to use that mass in E equals mc squared. But because of how Einstein did his work, he didn't use AMUs, he used kilograms. So we're going to convert the AMUs that we got on the previous slide, 0.59223 AMUs. We're going to convert that into kilograms. One AMU has a mass of this many, 1.6606 times 10 to the negative 27 kilograms. I have AMUs on the top. I'm going to put AMU on the bottom so that they cancel out. I'm going to put kilograms on the top, 1.6606 times 10 to the negative 27 kilograms. And when I do that math with my calculator, we get 9. Whoa, that is not a 9. Where did that come from? Let's try again. 9.8346 times 10 to the negative 28 kilograms. So this is our same mass, that same mass we find on the previous slide, just in kilograms instead. I'm going to use this as M in E equals mc squared. E equals mc squared. M is the mass that we just found. Energy is going to be equal to mass 9.8346 times 10 to the negative 28 kilograms. I'm going to multiply that by c squared. C is the speed of light. Speed of light is equal to 3.0 times 10 to the 8th meters per second. 3.0 times 10 to the 8th meters per second, but I need to square it. mc squared, mass speed of light squared. I do that math with my calculator because that's way too many numbers to do in my head. Energy is going to equal 8.85 times 10 to the negative 11 joules of energy is the amount of energy holding that nucleus of copper together. Amazing. All right, we're going to put E equals mc squared over. We're going to let all that big Einstein stuff ruminate in your brains for a little while, and we're going to flip over to this idea of rate of radioactive decay. So the rate, or how fast a radioisotope decays or releases its radioactivity, is different. So radioisotopes have different rates of decay. But when we're talking about any one specific radioisotope, like carbon-14, carbon-14's rate of decay is constant, and we call this its half-life. The half-life is how long it takes for half of the radioactive sample to decay. Half-life, right? Half of it has turned into something more stable. And this table shows us different radioisotopes and their different half-lives. So cobalt-60 has a half-life of 5 years. It takes 5 years for half of any sample of cobalt-60 to go through radioactive decay. We use cobalt-60 for chemotherapy. If I want to find tumors, I can use phosphorus-32. Its half-life is only 14 days. We use carbon-14 for archaeological dating. If I want to know how old a pot is, I can use carbon-14. Its half-life is, oh my gosh, 5,730 years. Iodine-131 that I use to treat disorders of the thyroid gland has a half-life of 8 days. Uranium-238, 4.5 billion years. That's a lot of years. We use uranium-238 to figure out the dates of very, very, very old rock samples. The oldest rock that we have ever found was 3.7 billion years old. We think that the solar system is about 4.6 billion years old. Amazing, amazing. And we know this because we can look at this uranium-238 stuff. All right, so we're going to practice this idea of half-lives. Half-lives is all about half is left over. So at time equals 0, I will have all my whole sample. After one half-life, only half of it is left. Here's where the math gets weird. After 2 half-lives, I don't lose the other half, but instead I only have half of the half that I had. So I'm going to take that 1/2 and I'm going to find a half of this half. That's a fourth. After 3 half-lives, I have a half of a fourth. That's 1/8. After 4 half-lives, that 1/8 that I had left, now I only have half of it remaining. I have 1/16 of the sample is still radioactive. We're going to do it again. Now I have a half of 1/16, that's 1/32. After 6 half-lives, now we've only got 1/64 remaining. So notice these powers of 2, right? 2 to the first power, 2 squared, 2 cubed, 2 to the fourth, 2 to the fifth, 2 to the sixth. That's our half-lives. 1/2, the number of half-lives, is how much, what fraction of our radioactive material is still radioactive. I think this makes a little bit more sense when we actually try to practice it. So we're going to look at barium-122. Has a half-life of 2 minutes. 2 whole minutes, right? Crazy sauce. So let's say that I have a sample of barium-122 and it's starting with 80 grams. So times 0 is 80 grams. My first half-life is 2 minutes later. In 2 minutes, I only have half of this left over. I have 40 grams. So 2 minutes after that, 4 total minutes, 2 plus 2 is 4. I only have half of this 40 grams left over. That's 20 grams. 2 minutes later, it's been 6 total minutes now. I only have half of 20 grams left. I only have 10 grams. 2 minutes later, 8 minutes. I'm down to 5 grams because half of 10 is 5. 2 minutes later, 10 minutes. The 10 minutes that it took us to set up our investigation to start using the barium-122, we only have 2.5 grams of radioactivity remaining. Those 80 grams of radioactive material 10 minutes ago, only 2.5 grams are still radioactive because of half-lives. My friends, you did it. Our objectives that we achieved. We defined radioisotope and transmutation. Transmutation when one element turns into another, like when carbon can turn into nitrogen during beta decay. We identified those radioisotopes. Little guys, they're stable if they're equal. big guys are all radioactive. The middle guys, we want more neutrons than protons to be stable. We talked about some of those applications of radioactivity, power, and Geiger counters and smoke detectors. We identified different kinds of radioactive decay. We talked about alpha and beta. We talked about beta positive, which is also called positron decay. We looked at electron capture. We looked at fission and fusion, and we talked about that amazing gamma radiation that can be released, lots of energy. We balanced some of those nuclear equations. Tops and bottoms need to match on both sides of the arrow. We used E equals mc squared energy mass, that mass defect, and then speed of light squared. And then we just talked about half-lives. Good work today, my friends.